the notes for 10.3. So our goal is going to be to find the area of regular polygons. And remember, regular polygons have all angles and sides that are congruent or of equal measure. So we're going to be finding the area of regular polygons, but there's some vocabulary we need to cover with this first. And in class, if you were absent, we did use highlighters, and we were highlighting things because it's very helpful when you're learning new stuff to highlight stuff that's new. So a new word for us is called an apothegm. An apothegm, some people call it an apothegm, I call it an apothegm, is the height of one of the triangles made. So right here I have my regular pentagon, and in here at the center, if I were to head out and connect a center to a vertex and a center to a vertex, you'll see that I will create 5 triangles in there. The height of any one of them, so here's, again, the height is perpendicular to the base. It's called an apothegm. So when we ask for the apothegm, it is the height of one of those triangles. And it always cuts a central angle in half. So in here at the center, we have 5 angles. 1, 2, 3, 4, 5. When you drop the apothegm, it cuts that angle in half. To get the measure of that central angle, because we're going to need it sometimes, well, it has to do with the fact of in here I have a circular figure when I go around there made by 1, 2, 3, 4, 5 angles pieced together. So I would, to get that one angle, I take my 360 around the whole circle, divide by 5, and I'd say the central angle of a regular pentagon has a measure of 72 degrees. Okay? Now how do I get that in general? I take 360 all the way around the full circle, and I divide it up amongst the number of angles in there, which is actually equal to the number of sides. So n could be number of sides. All right? So finding the central angle is very easy. And then remember, I've said that the apothegm, so here's one central angle. I just drew it in red right here at the arc. When I drop the apothegm, it's going to cut that 72-degree angle, because all of these are 72, right? All of them, dropping an apothegm cuts it in half. So for my central angle, it'd be the 72-degree central. Sorry, for my measure of angle DOP, it's going to be 72 and half of it, because the apothegm, when I drop it, cuts it in half. So if ever we need that angle, we know how to get it. And from the center out, okay? So when I draw from the center out, it's called a radius. Kind of like the radius of the circle in which this would sit. If I circumscribe this figure, it'd be inside a circle, and this would be the radius of the circle. This is a radius, 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 radius. They are all equal. So a radius goes from the center to the vertex. All right, so let's go over here and practice a little bit about this vocabulary. So this guy is a regular. Count up the sides. There are 6 of them. Okay, so this would be a regular hexagon. My n in this scenario would be 6. When it says draw the radii, I go to the center and I head out to a vertex. There's one of them, like the spokes on a wheel. 2 of them, 3 of them, 4 of them, 5 of them, 6 of them. All of those are radii. What's the measure of the central angle? 1, 2, 3, 4, 5, 6 of them around the circle. So we do 360 divided by 6 for a 60-degree central angle. I'm going to go put that just on what I call the front triangle. I like to call this one, it's just sort of front and center. I like to call it the front. That's 60 degrees. Now, with the hexagon, each of these triangles is actually a special kind. Because remember I told you the radii are the same. And if the radii are the same, we have an isosceles triangle. I like to say that word. And the base angles are the same for an isosceles. And the angles in a triangle add up to 180. So if I did my 180 minus the 60-degree central angle, I have 120 degrees for these two base angles down here to share equally. So this is a special case. With the hexagon, we get an equilateral triangle in there. All 6 of them are. So we know that all of those angles are 60 degrees. Only for the hexagon, right? But it helps us do little shortcuts for our hexagon. Next, if I drop my apothem, what is the apothem? We already said up in our vocabulary section that it is the height of one of those triangles. Well, again, I'm just going to focus on the one that is front and center is what I call it. You're going to hear me saying, pull off the front one. I'm going to drop that apothem at a 90-degree angle. This is my apothem. Remember, all of these are called radii. So I'll put a little, that's not going to be in our formula. We're not even going to need it, but it's good to know the vocabulary. So this right here is my apothem, the height of one of the triangles. I did that, and it says the front one, so I did it. I call that the front one. It says, what kind of a special triangle is made? Well, remember I said when you drop that apothem, you cut that central angle in half. So we're going to have a little special 30-60 that we're going to be working with when we have a hexagon. I'm going to go shade in my special right triangle made when I dropped my apothem. It's right here. You're going to be focusing on this guy quite a bit. All right, so just some vocabulary before we get to our formula. So next up at the bottom of the page, well, how do we find the area of this? Well, it's kind of an advanced process, but for this first part, it's not going to be too bad. Our formula for the area is that we do 1/2, and then we have 3 ingredients that we need, 3 variables. We need the A, that's going to be the apothem, the height of one of the triangles made. We need the S, which is going to stand for the length of a side. So go ahead and put side length. And we need the N, and that's going to be the number of sides. So if it's a hexagon, it's a 6. I did pause the video there for a second, but again, that last variable, the N, and I've been sometimes calling these ingredients, they're kind of what I need to be given or need to find in order to dump them into my formula or my recipe. And N is the number of sides. 6 for a hexagon, 8 for an octagon, you kind of get the idea. So let's do first case scenario. Best thing, recall when we were working with our other 5 formulas, it was really nice when they were giving me all of the variables. All I have to do is dump them in, okay? And so this one over here says we've got a regular decagon. I can count the sides, but I know deca means 10. So they're telling me the N, or giving me that ingredient. The apothem is the height of one of the triangles made. Now there's going to be 10 of them made in here, but I'm going to focus on this one that I call front and center because that's where the information is. So the height was given to me. It was a 12.3 is the height of that front and center triangle. That's my apothem. They gave it to me, and that perpendicular box is kind of how you know that, by the way. And then S stands for the side length. Well, they gave me that down here. So they gave me everything I need. All I need to do is go dump those in to my recipe or into my formula, which says I do 1/2 times the apothem times the side length times the number of sides, which means I do 1/2 or 0.5 if you like it. My apothem was, 12.3. My side length was 8, and it was a decagon, so my N was 10. I run that through my calculator, and I got exactly 492 square inches. That was lovely because everything I needed, I had. We're not going to practice that a lot because if you have it all, you just dump it in and go to your calculator. But what if stuff is missing? So I'm going to go a little slower. If one of your ingredients is missing, So remember, our formula says to get the area, we need to do a half, that's a constant, times whatever the apothem is, times whatever the side length is, times the number of sides. Now it says if one of the variables is missing, this they have to give you. Either they give you a picture and you count them up, or you have the word for it. So that you're never going to be in search of. All right? So I need to, on this one, figure out what did they give me, what didn't they give me, and how do I find my missing pieces. So I, again, like to focus on, that's a picture of a hexagon, but it has 6 triangles in there. I'm going to pull this one off and make it bigger and just work with this one. I'm going to go put the 18 over here. This, remember, is a radius. It's not in my formula, unfortunately. In my formula is the height of one of the triangles, which we call an apothem, and the side length of the hexagon, which would be this. So again, I'm kind of pulling this one down and out so I can work with it. Now remember, the beauty of the hexagon is that the radii are the same. This is a 60-degree angle. And then we said, well, then this is 60, and this is only for the hexagon does this happen, but it's nice because it creates an equilateral triangle. And if I know it's equilateral, then not only is this 18 and this 18, but my side length is 18. So actually, I get to steal it. Next up, when I drop the apothem, I would have split the side in half. Now, some people will say, well, LaRue, this is a 30/60. If I have the hypotenuse, don't I just divide by 2 to get the short side? And then won't I just double it since that's halfway? And I say, yeah. So you could get there even if you didn't recognize it was equilateral. Now, I now have my side. This whole side right here is 18. So is this, because that's an equilateral, equal angular triangle. But now I need to go from short to long on the 30/60, which we put on our note card that we do the short times the square root of 3. So short times the square root of 3. Now that I have my 2 missing in green and the one that's never missing in blue, I'm ready to go and use my formula. I am going to do 1/2 times A, again it's 1/2 A S A. It's not writing right there for some reason. All right, so 1/2 of A would be 9/3 times S is 18. You can go right in order if you show your work like that. Now to the nearest tenth, I just go to my calculator and I enter it all. Make sure if you have a calculator that puts a left parenthesis here, you need to close it. Okay, so you're going to do 1/2 times 9/3 times 18 times 6, and you're going to get an 841 point. It looks like I wrote an 8 there to the nearest 10. Now, if I said simplest radical form, what that means is you do everything except that root 3. You keep the radical or the root in your answer. So I'm just going to drop that root 3 down, and then I do the rest on my calculator. I do 1/2 times 9, skip over the root 3, times 18, times 6. And if you do that on your calculator, you're going to get a 486 times the square root of 3. This answer and this answer are basically the same. This one's been rounded. This one's exact. All right? So that one was a little trickier than the first one I did because you weren't given everything you need. So let's go take a look at the next one. It says, well, what about the square? We might say, LaRue, a square is side times side. Yeah, if you know the side. So, right here, I don't know the side. I've been given, again, if I were to draw my radii, I'd have 4 triangles in here. And I was given the height of one of them. And again, this little box is kind of the kicker to that. This is my apothem. So I know the apothem on this one. However, we do not need to do 1/2 ASN, because if we were, we'd need to find the side length. And if we knew the side length, right, we could just use our elementary school formula for area of a square. So watch this. If you know the hypotenuse is 5, and it goes from the middle to the edge, right? For a square, it's going to be the same this way as well. So 5 and 5. Well, if I take my other color, maybe blue, and I draw the whole thing, which is 10, that means it's 10 there, it's 10 here. More importantly, it's 10 over here, which is the side length. And the sides on a square are the same. So a side length is going to be 2 times my apothem, which in this case is 2 times my 5 or 10. So now that I know a side of the square, I'm just going to do my middle school formula for area of a square, 100. Now if I did the 1/2 ASN and found all that stuff and plugged it in, I'd still get 100. Again, we can use some shortcuts with this square. All right, so my next shortcut that I want to show you is, what if you're given this piece on the square? And I would ask you, in class I would have said, what is this? Is it a side length? Is it an apothem? Is it a radius? Is it a height? What is it? And remember, when we go from the center to the vertex, these are called radii. There are 4 of them on my quadrilateral. There are 5 of them on my pentagon. They're the spokes of the wheel. You don't see that little right ankle box. It's not an apothem. This right here is a radius. So it says the 10 is not the side length. It's not the S. It's not the apothem. However, every square is a rhombus because all of its sides are congruent, and that's what we need for a rhombus. For a rhombus, the diagonals are congruent and they bisect each other. So if half of it is 10, the other half is 10. And they're congruent on a square. So that means this is 10 and this is 10. So if they give me this radius, which is actually half of the diagonal, I'm going to treat my square as a rhombus and use the rhombus formula, which says we do 1/2 of diagonal 1, which would be 20 all the way across there. So I do 1/2 of 20 times the other one, which is also 20. It goes back to our earlier chapter, I think it was 6, on quadrilaterals, that said a rhombus has 4 congruent sides. Well, a square is a rhombus, right? So I can use this formula on any rhombus. Well, if I knew this was 10, I also know the diagonals bisect each other, so 10 and 10. We also know for a square, diagonals are congruent, so another 10 and 10. So it's a little shortcut we have for if we know the radius, might be no card worthy later. Just get the diagonals by doubling. So now a little practice here on the bottom. All right, so we've got 2 triangles and a hexagon. All right, so remember our formula is 1/2 for the area. We need 1/2 times the apothem times the side length times the number of sides. This will never be hidden on me. 3, 3, 6. Okay, so for all of these, we don't have a shortcut. We only have the shortcuts for the square. So I'm going to go over here and write A equals, S equals, N equals. I'm going to go on all of these. I'm going to write A equals, S equals, N equals. A equals, S equals, and N equals. I'm going to go fill in those N's first because they can't hide them on me. Number of sides on a triangle, 3. Number of sides on a triangle, still 3. Number of sides on a hexagon, 6. Then I like to draw the radii. I think it helps me see it. So I'm going to switch colors, and in blue, I'm going to go draw the radii on, excuse me, all of mine. Center to vertex, center to vertex, center to vertex. Sorry, excuse me, I'm going to get a drink of water. So what that tells me on this one is that 2 is pointing to a radii. That is not in my formula. That's kind of a bummer. I'm going to go, so I'm not going to put that 2 anywhere. But I'm going to go to my next one and do the same thing. Center to vertex, center to vertex, center to vertex. Well, that 7 is the height of one of those 3 triangles. That's my apophysis. That's kind of nice. Same here. If I were to draw my radii, I'm not going to draw all 6 of them. I'm just going to go to what I call this front triangle. You can see that little right angle box there. It's the height, so they're giving me the apophysis again. All right. So that's kind of what I was able to get easily is what I wrote down. So let's go to this triangle over here. All right, the very first one. I need to figure out the apophysis and the side length. What I like to do is pull off and enlarge one of these triangles up here. So I'm going to do what I call the front one. I'm going to pull it off and work with it down below. I'm going to pull this one off, and I'm going to work with it down below. I'm going to pull this guy off, and I'm going to work with it, because it gets small to work in that whole figure. So I'm going to blow that one up like this. So that yellow is this yellow. I'm going to label what I know and find what I need to find. So all the spokes of the wheel are 2. That'd be this guy, not my formula. Unfortunately, I need the apophysis and I need the side length. All right, so how am I going to get that? Well, it comes down to special triangles. So let's go back up here. If I were to go in here and find my central angle, I would do 360 divided by 3 is 120. But when I drop that apophysis, I cut it in half, so I have a 60. What a shocker, right, that we've got the 30, 60, 90? Well, the apophysis is the short side, and I have the hypotenuse. And we have written down that we divide the hypotenuse by 2, which means my apophysis is going to be 1. Boom. Now, how do I get this entire side length? All I'm going to do is figure out half of it, because it's the long leg on my 30, 60, 90, and I have the short. And we have on our note card that we multiply by root 3. And 1 times root 3 is root 3. Well, that's halfway, so I need to double it to get the whole side. Now those ingredients go into my formula. I do 1/2. Where can I write it? Down here. 1/2 times the apophysis, 1, times the side length, which is 2 root 3, times the number of sides. And I just plug it in. And again, if it's a simplest radical form, we keep that root 3 in our answer. We don't touch it, and we do the rest. We do 1/2 times 2, and then we do that times 3. So it looks like I'm just going to have a half of 2 is 1 times 3 is 3. So there's my final answer. A little tricky, all right? I would challenge you to try this next one on your own. But again, this one I'm only missing the side length, so it's a little easier. I don't know that I need to pull that yellow one out because the 7 was on the apophysis. The apophysis is the short side. The long side, because again it's going to make the 30, 60, 90, is the short times the square root of 3. Well, that's halfway. Again, I need a side of the triangle. So I need to do 2 of those, which would be 14 root 3 for the side length. And then again, I just plug them into my model. My area is 1/2 times the apophysis times the side length times the number of sides. Put this in your answer and do the rest of it on your calculator. And if you multiply to half times 7 times 14 times 3, you get 147 root 3. Our last one, the hexagon. All right, so that 4 root 3, I'm going to draw again. I'm pulling that. I should do it in blue on this side there, right? Or is that not writing in blue? I don't know. It's weird. It's blue, blue. I don't know. Oh, coming back to red. Well, there we go. Now I'm blue. All right, so I'm pulling this guy out and making it bigger. Okay, the 4 root 3 was on the apothem. So I already put that in here. There's 6 sides. I need to get the side length. I need to figure out how long is a side. Well, my side length is going to be all the way across. All the way across. I have the 30, 60, 90 again, because again, we said the hexagon, we take that 60-degree central angle, cut it in half, we've got the 30. Well, what side did they give me? They gave me the long side. Well, that's kind of nice. And it's in a nice format because to go from long to short, I divide by root 3. I just get a 4 here. Again, that's halfway across, so I need to double it for the side length. My side length will be 8. It's 4 here, here, 4 here, here, 8 all the way across. And then back into my formula. My area is 1/2 of my apothem times my side length times, and again, sometimes I use parentheses, sometimes dots. I like parentheses better because dots look like decimal points, but just in case you don't. If it says as a decimal or round, you do it all on your calculator. But again, if it says simplest radical form, we put the root 3 down, and we do the rest of it on our calculator. We would end up getting a 96 if we did 1/2 times 4 times 8 times 6. 96 root 3. And that's it. Kind of a hard section. We'll be doing more with it on Monday the 10th. Your assignment is in Schoology, and it is the 3rd one. All right, so it'll be 10.3s in Schoology. Have a good one.